Today we're going to continue our talk in Chapter 8, but this time about improper integrals. So improper integrals are like integrals where you are trying to integrate to infinity. So it's an integral that has one or both of its limits of integration as infinity, or there is a discontinuity within the limits of integration. So we're going to look at this in two pieces, where one of the limits of integration is infinity, and then when there's a discontinuity. So what we're actually talking about here is we're talking about like integrating from 0 to infinity of this curve e to the negative x over 2. Does it have an answer? Like, can I find the area under the curve if I'm going to infinity? What allows us to figure that out? Okay. Well, the first types of improper integrals are when one of your limits of integration is infinity, or both of them are. And what you can do is you can look at the limit as a variable approaches infinity of that integral, and if that limit exists, then the improper integral is said to converge to the limit. Otherwise, the improper integral diverges. So notation is important in this situation of problems, as well as being careful and showing all of your work. Okay, so in this first case, this is improper because one of the limits of integration is infinity. All right? So what I'm going to do is I'm going to say, all right, I'm going to look at the limit as some variable approaches infinity of the integral from 1 to that variable of dx over x. Now, what you want to think about is you're integrating from 1 to infinity, right? And you made that infinity a. So you're actually coming at infinity from the left-hand side. So I put a little infinity from the left-hand side as I look at the limit. All right, so now I integrate. So I haven't evaluated the limit, so I keep the limit there. The integral of dx over x is the natural log of the absolute value of x. We're evaluating from 1 to a. So that would be a limit as a approaches infinity from the left of the natural log of the absolute value of a minus the natural log of the absolute value of 1. So really this is the natural log of infinity, which is infinity, minus 0. Well, that does not give me an answer, so therefore I can say that the integral from 1 to infinity of dx over x diverges. So I'm only going to get an answer whenever I get a number answer from my limit, not an infinity answer. Let's look at another example. This time my infinity, same thing, the infinity is at the top. So I usually use the letters A and C. I try to stay away from B because B looks like a 6 whenever I write it. So I just try to stay away from it. So the limit as A approaches infinity, again from the left, of 1 to A of dx over x squared. So that would be the limit as A approaches infinity from the left. And I integrate this, that's going to be negative 1 over x from 1 to a. So that would be the limit as a approaches infinity from the left of negative 1 over a minus a negative, so plus 1 over 1. Well, we know when we plug in infinity in the denominator of a fraction, that means that fraction is going to go to 0. So this limit's really 0 plus 1, or 1. So what that means in this case is that the integral from 1 to infinity of dx over x squared does converge. It has an answer, and it converges to 1. So you might want to wonder why the first problem did not converge, and it was 1 over x, and the second one did, and it's 1 over x squared. If you think about it, 1 over x and 1 over x squared are graphs that are looking like this, but 1 over x squared is going to get closer to the x-axis faster. So I think that the speed of that going to the x-axis allows it to converge rather than diverge. So in number 3, we again have it's improper because we have a limit of integration that's infinity. This time it's negative infinity, and it's at the bottom. So this time, whenever I set up, I'm going to do the limit as a approaches negative infinity from a to 0. So since I'm going from a to 0, I'll approach that negative infinity from the right of e to the 3x dx. So that's the limit as a approaches negative infinity from the right. Integrate e to the 3x dx, so that'd be 1/3 e to the 3x from a to 0. So that's going to be the limit as a approaches negative infinity from the right of 1/3 e to the 0 minus 1/3 e to the 3a. So a is negative infinity. If you think about e to the x going to negative infinity, that's going to be closer and closer to 0. So that's 0. Anything to the 0 power is 1, so that's 1/3. 1/3 minus 0 is 1/3. So we can say that this integral, this improper integral, actually does converge, and it converges to 1/3. Okay. One more example. So this is in a case where you have both your limits of integration are at infinity. So you just have to break them up. What's a convenient place to break them up? Well, you could break it anywhere. You could go from negative infinity to 16 and from 16 to positive infinity if you want. It's kind of an odd place to stop, but kind of a natural place to stop would be 0, just because it makes the problem easier. So we'll do the limit as a approaches negative infinity, and this would be from the right. So we're going to go from a to 0 of x cubed dx, and we're going to add the limit as c approaches positive infinity, and this would be positive infinity from the left, and this would be go from 0 to c of x cubed dx. Okay, so when I integrate, I will get the limit as a approaches negative infinity from the right of x cubed, so that's going to be x to the 4th over 4 from a to 0, plus the limit as c approaches positive infinity from the left of x to the 4th over 4 from 0 to c. So when I plug in 0 on top, I'll get 0. When I plug in infinity on the or a in the bottom, I'll actually get when I plug in infinity, I'll have infinity over 4, so that's still infinity. Plus, when I plug infinity on top, I'll get infinity minus 0. So I get this indeterminate form, so that means that this integral does not converge. It would actually diverge because it's not actually an answer. So the integral from negative infinity to positive infinity of x cubed dx diverges. Okay? Much like I did not kind of specifically talk through all of these pieces of information for improper integral cases, this is where you have a discontinuity within your limits of integration. So your function is defined, but somewhere within that function there's a discontinuity. So I think the easiest way to deal with this is to look at examples. All right, so when I integrate from 0 to 1 of dx over the cube root of x, well, at 0, that's going to be undefined. So this is improper because the function, the integrand, is undefined at one of your limits of integration. So what I actually have to do is I have to look at the limit as a approaches 0 of the integral from a to 1, and I'm going to rewrite that as x to the negative 1/3 dx, just to make it easier to integrate. And remember, I'm going from a to 1, so I would be approaching a from the right. So 0 from the right. So when I integrate x to the negative 1/3, see, I still need my limit in here. That's going to be negative 1/3 plus 1 is 2/3 divided by 2/3, or 3/2 times x to the 1/3 from a to 1. So that would be the limit as a approaches 0 from the right of 3/2, plug in 1, the cube root of 1 is 1, minus 3/2 times the cube root of a, and the cube root of 0 is 0, so this is really 0, but this does have an answer because it's 3/2 minus 0, or 3/2. So we would say that the integral from 0 to 1 of dx over the cube root of x converges, and it converges to 3/2. Okay? So you can have an improper integral because one of your limits of integration at the end is makes the function undefined, or it could be within your limits of integration. So I know that here x is undefined, or the function is undefined at 0. So I have to break this up. So I have to go from negative 1 to 0, and from 0 to 2 of dx over x cubed. So that means I'm going to have to do two different limits there. So I'm going to say that's the limit as a approaches 0, and so this is from negative 1 to 0, so that would be from the left of the integral of dx over x cubed, plus the limit as c approaches 0. This time we're going from 0 to 2, so we'd be going from the right of the integral of dx over x cubed. So when I integrate, I will get x to the, says x to the negative 3, so it's x to the negative 2 over negative 2. So that is negative 1 over 2x squared. Don't forget there's still a limit here. A approaches 0 from the left, from, oops, I didn't put these in here. This is negative 1 to a, and this is c to 2. So this is negative 1 to a, plus the limit as c approaches 0 from the right of negative 1 over 2x squared from c to 2. So if I plug in a, that's going to be 0. So 1 over some very, very small number is going to be a really, really big number, so that's going to be infinity. And then when I plug in negative 1, I will get negative 1/2, so minus a negative 1/2 becomes plus 1/2. Plus, when I plug in 2, I will get negative 1/8 minus, when I plug in 0, I'll get a really, really big number, but it's minus, so it'll be an infinity. So this whole thing's going to be infinity, which means that my integral is going to diverge. So there's no answer to that integral. That improper integral, I should specify. Okay, a couple more examples here. All right, 7. So we can see that one of my limits of integration is infinity. So this is like the first case. So I do the limit as a approaches infinity, so I'm going from 0 to infinity, so that'd be from the left, of the integral of 2 dx over x squared plus 4x plus 3. Well, if I do a u substitution, I would get 2x plus 4 on the bottom, and I have no way to handle that on top. So I'm actually going to have to use partial fraction decomposition to integrate this. So I'll look at the fraction 2 over x plus 3 times x plus 1, which is what x squared plus 4x plus 3 would factor into. And so that would be a over x plus 3 plus b over x plus 1. Multiplying through by the common denominator, I'll get 2 equals a times x plus 1 plus b times x plus 3. So if I let x equal -1, the a term will add out, and I'll get 2 equals 2b, so b is 1. If I let x equal -3, the b term will add out. I'll have 2 equals -2a, so a is -1. So this integral becomes the limit as a approaches infinity from the left of 0 to a of -1 over x plus 3 plus 1 over x plus 1 dx. So that's the limit as a approaches infinity from the left of negative natural log of absolute value x plus 3 plus natural log of absolute value of x plus 1 evaluated from 0 to a. So if I plug in infinity, I'm going to get the natural log of infinity. So that's going to be infinity. It doesn't matter what else this stuff is. That's going to be infinity. So this integral is going to diverge. So I'm going to write up here. Okay? Because I ran out of space. Okay, 2 more examples. First one. Here again, I have both of my limits of integration are infinity, so I'm going to break it up. Again, a good place to break it up is 0. So I'm going to say, I'm going to do the limit as a approaches negative infinity. So I'm going to go from a to 0 of dx over 1 plus x squared, plus the limit as c approaches positive infinity. So I'll go from 0 to c of dx over 1 plus x squared. So here I'm going from a to 0, and here I'm going from 0 to c. So a is going to approach from the left, c is going to approach from, a is going to approach from the right, c is going to approach from the left. Okay. Well, what is the integral of 1 dx over 1 plus x squared? Hopefully you remember that's inverse tangent. So that's inverse tangent of x, evaluated from a to 0, plus the limit as c approaches infinity from the left of inverse tangent of x from 0 to c. So when I plug these in, I will actually have the limit as a approaches negative infinity from the right, the inverse tangent of 0 minus the inverse tangent of a, plus the limit as c approaches infinity from the left, of the inverse tangent of c minus the inverse tangent of 0. Well, we know the inverse tangent of 0 is 0. Do we know when the inverse tangent is infinity, or negative infinity, I should say? And yes, I do if I think about the tangent graph. So tangent graph goes like this, and this is pi over 2 and negative pi over 2 for my asymptotes. So it would be negative infinity at negative pi over 2. So that's going to be negative pi over 2. So it's going to be minus a negative pi over 2. Plus, it's going to be positive infinity at positive pi over 2 minus 0. So that means I'm really just adding 2 pi over 2, so I get pi for my answer. which tells me that the integral from negative infinity to infinity of dx over 1 plus x squared is, in fact,
That's hilarious.
pi. I'm going to stop there. We'll do the last example in class together, and hopefully that wasn't too bad, 20 minutes. Hopefully that wasn't too bad.